Hey everyone, Chang here and welcome to my channel. Today I'm actually going to be going over a topic that was covered in a previous video. That's right, today I'm going to go over several more properties of exponents that I didn't cover in the previous video. By the end of this video, you're going to know what to do when you have exponents to the zero power, to the negative power, and what to do with multiplication and division problems taken to the exponential powers. First, let's recap on what exponents are. Exponents are nothing more than repeated multiplication. Here's an expression of an exponent. Now, notice that there is a large number and a small number. The large number is known as the base. That's the number that's being multiplied however many times you desire. The exponent, the small number, that's telling us how many times to multiply that base number. Now, if you have not checked out my previous video, I suggest you do so. There I covered some of the basic properties of exponents. Today we're going to actually start off with this property. Here we have a to the zero power equals 1 as long as a is not equal to 0. Well, don't let this variable scare you. This is a way to generalize number. What this is saying is that for some number a could be any number as long as it's not 0. This property is true. That means if you take that number to the 0 power, the answer is actually going to be 1. That means if you take 7 to the 0 power, it's equals 1. If you take negative 200 to the 0 power, it equals 1. And if you're not satisfied, you can actually take 17 billion to the 0 power. Guess what? Still equals 1. And we can keep on plugging in all the numbers we want, all the way until we grow white hair, grow old, and die, and it still would work. Now, the only thing that doesn't work is if you have 0 to the 0 power. 0 to the 0 power is a special case. It actually does not equal 1. Now, what it actually equals is undefined. There are some people who argue differently, but yes, it is just undefined. Now, what does undefined mean? Well, there are technical differences, but basically undefined in mathematics term mean that it will result in error if you do so. So you're technically not allowed to have 0 to the 0 power. Does not work. Now, the second property is actually very interesting. Here it is. We have 2 to the negative a equals 1 over 2 to the positive a. What this basically means is that if you have 2 to some negative exponent, it is basically the same thing as the fraction 1 over 2 to the exact same exponent, but the positive version of it. Now here's the thing. It doesn't actually have to be 2. It could be any number you want. Well, any number except for 0, but any number you want. I'm only using 2 here because I want to limit the amount of variables that we're going to use. I want you guys to get the concept and not get confused by too many variables. So what this is saying is that if you have, for example, 2 to the negative 4, that's the same as 1 over 2 to the 4th. Or, like I said, we can use different numbers. We can have 3 to the negative 6. That is the same as 1 over 3 to the 6th. Now, I wanted to introduce these two properties before I went to the explanation of it because this explanation hopefully will cover both properties. Let's begin. Let's use this example as an explanation. I'm going to use a lot of different expressions, so hopefully it's easier to follow along. Let's start off with this. 2 to the 5th power. Well, that's just 2 times itself 5 times. That's fairly simple for us. 2 to the 4th power is 2 times itself 4 times. 2 to the 3rd power is 2 times itself 3 times. 2 to the 2nd power is just 2 times 2, or 2 times itself twice. 2 to the 1st power is just 2. Well, from there, we're actually going to list some more. We have 2 to the 0 power, 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. Well, I'm not going to tell you what they are just yet, but we're going to start off with this. 2 to the 5th power is 2 times itself 5 times, whereas 2 to the 4th power is 2 times itself 4 times. The difference between these two are just basically a multiplication of 2. So, 2 to the 4th times an extra 2 will give you 2 to the 5th. Well, actually, we're going to go backwards on this. Starting from 2 to the 5th, to get to 2 to the 4th, we have to get rid of this extra multiplication of 2. In order to do that, we actually have to do the opposite. which is to divide. So we're going to divide by 2. 2 to the 5th divided by 2, the 2 cancels each other out, and you have 2 to the 4th. Well, we're going to go a step further. 2 to the 4th, to get to 2 to the 3rd, we're going to have to get rid of a 2, so we're going to divide by 2 again. Again, we're going to go from 2 to the 3rd to 2 to the 2nd by dividing by 2, and from 2 to the 2nd to 2 to the 1st, we're going to divide by 2. Well, from this reasoning, we can sort of guess what the pattern is. Every time we're going backwards a step, we're dividing by 2. Well, if we want to go from 2 to the 1st power to 2 to the 0 power, the logical step would be to divide by 2. Well, 2 divided by 2 in this case is 1. So yes, 2 to the 0 power is 1. Now, we're going to go even further than that. To jump from 2 to 0 to 2 to the negative 1, we're going again one step backward. So, 1 divided by 2 in this case is just 1 over 2, or 1/2. Let's go one more step. So from 2 to the negative 1 to 2 to the negative 2, we're going to divide by 2. Well, 1/2 divided by 2 is actually 1 over 4. But I'm going to rewrite it so that's easier to see. That's just basically 1 over 2 squared. Well, from 2 to the negative 2 to 2 to the negative 3, we're going to divide by 2 again. Well, 1/4 divided by 2 is basically 1 over 8. Well, I'm going to rewrite it again. That's basically 1 over 2 squared divided by 2, or 1 over 2 to the 3rd power. And you can use this reasoning with any numbers other than 0. If you use 0, well, it's not really going to work. And the reason it doesn't work is quite simple. The reasoning that we're using is division. We're dividing by that number. Since we're working with 2, we're dividing by 2. If we're working with 4, we're dividing by 4. If we're working with 49, we're dividing by 49. But if we try to use this logic with 0, it doesn't work. We can't ever divide by 0. Now, this next property actually shows two different versions. But in all honesty, these two versions are almost exactly the same. It looks slightly different, but they are the same. Here they are. The first one is a times b parentheses squared is actually the same as a squared times b squared. The second version is a divided by b parentheses squared is actually the same as a squared divided by b squared. In this case, the exponent of 2 can actually be switched out with any other number and it will still work. So let's use this as an example of the property. 6 times 2 parentheses squared is the same as 6 squared times 2 squared, which is equal to 144. Well, if we use the other version, 8 divided by 4 parentheses squared is the same as 8 squared divided by 4 squared, which is equal to 4. Now, it doesn't just work with exponents of 2. Guess what? If you change the exponents to 5, 79, 1,483, right? The properties will still work. Now, the reasoning for the property is actually quite simple. Let's use the first example. Here we have 6 times 2 parentheses squared. Well, that's just basically saying that you have 6 times 2 parentheses times itself twice. Well, 6 times 2 parentheses times 6 times 2 parentheses. Well, let's get rid of the parentheses. We don't have any need for them right now, which is going to make it 6 times 2 times 6 times 2. Well, I'm going to rewrite it so that it's even more obvious. This equals 6 times 6 times 2 times 2. I just rearranged the numbers. Now, we know that 6 times 6 is just 6 times itself twice, or 6 squared. And 2 times 2 is just 2 times itself twice, which is 2 squared. So it's actually equal to 6 squared times 2 squared. Now, this reasoning again works with any number and any exponents. Now let's go over some of these common mistakes that follow along these properties. Luckily for us, although these are common mistakes, as long as we know that they exist and we are careful, they're easily avoidable. The first common mistakes follow along the line of something like this. 7 to the 0 power equals 0. Well, that just means 7 times itself 0 times. Now what the heck does that mean? That means 7 is not even multiplying itself even once. So since that's the case, that 7 really exists, it only makes sense that the answer is actually 0. That's not the case at all. From the first property, we see that any number to the 0 power is actually 1, unless it is 0 to the 0 power. In this case, is actually undefined. The second common mistake has to do with negative exponent. Because we're working with negative exponents, some of us are more inclined to think that, well, with negative exponent, the answer must somehow be negative. Now that's not the case. Here's some examples of mistakes that I've seen. Now for each of these examples, I'm going to compute both sides so that you guys can compare the answers and realize that they are drastically different. So to avoid this common mistake is quite simple. Just because you're working with negative exponent, it actually has nothing to do with whether the answer is positive or negative. The third common mistake has to do with the distribution of exponents. Now, here's an example. Here we have a plus b, parentheses, to the third power. The basic assumption should be that it equals a to the third power plus b to the third power. Just distribute the exponents. Well, that's not the case. The only reason that I was able to do it in the beginning of the video is because inside the parentheses, we're working with a multiplication and division only. If it happened to be addition or subtraction, this will not work. Now that was pretty simple, pretty straightforward, not too bad, not too complicated. Let's do this.
1,
Just a keynote, I will have the answers in the description for those of you guys who are curious and want to check your answers.
3,
Thank you for sticking with me until the end of this video. Let's just basically summarize what we went over. Now the first property for this video is the idea that any number to the exponent of 0 is just equal to 1, no matter what the number is. The only exception is that if the base itself is 0, then 0 to the 0 power is actually undefined. The second property states that if you have some number to the negative exponent, that's the same as 1 over that exact same number to that exact same exponent, but the positive version of it. The only exception is that if the base is 0, then it is undefined. It doesn't work. Remember, we can never ever divide by 0. The third property is that if you want to distribute the exponents, make sure that the inside of the parentheses are all multiplication or all division. If there's any hints of addition or subtraction, you are not allowed to do so. Now, with each and every one of these properties, there are common mistakes associated with these properties. The first one has to do with the 0 exponent. Because it is a 0 exponent, it's so easy to assume that the answer should be 0. That's not the case. From the first property, we know that any number to the 0 power is actually 1. The only exception is 0 to the 0 power, in which it is undefined. The second common mistake has to do with the negative exponent. Because it is a negative exponent, it might incline the answer to be negative. That's not necessarily the case either. The negative exponent just tells us how to orient the problem. It has nothing to do with the idea of whether the answer is a surefire positive or a surefire negative. The third common mistake is the distribution of exponents. If the inside is addition or subtraction, never ever distribute the exponent. If you distribute the exponent, it's a guaranteed error. Now lastly, please like, comment, and subscribe to let me know that you are tired of discussing about exponent. You're tired of hearing me talk about exponent. You never ever want to see an exponent again. So we are done with exponent for good, right? Maybe?